Hello everyone, welcome to another lecture on system engineering. Previously, we defined a system. Simply, we said a system, a set of interrelated entities and components that they perform a function. The system does something. Something emerges from the system, which we call it an emergence. So pay attention to every word in this definition. A set of interrelated components or parts or entities that perform a function. Something comes out of the system, which we call it an emergence. A simple example is an elevator. An elevator simply is some components like a shaft, cabin, motors, column, cables, and so on. It's a complex system, but it does something which we can understand easily. The emergence of this system is to take a person from one floor to another. Think about a system like image recognition system. It can recognize a cat's and dog's image and label it for you. What it does is very simple to label the images. But what is inside this system is complex. If you've learned machine learning, you know you need to apply some convolutional neural networks to do the image processing. There are some math and some machine learning algorithms. But what is important for us is to understand easily what this system does. And then later, we'll focus on the component that they do that function for us. So let's have a little discussion. Look at these two systems. Both do the same function. They are bicycles, an early invention of a bicycle and a more modern bicycle. So the question is, what aspect has become more complex in the modern bicycles? Perhaps the material, the adjustment of the seats, adding gears, and maybe the shape and the geometry. But the more important question is, what drives these changes? Perhaps safety, maybe the need for better performance, or maybe some new technologies and materials drives us to design a bicycle which is more efficient. Perhaps it's lighter with better and stronger material. Now, can you think about a system that become more complex and also think about what made it more complex or what is behind its increasing complexity? I can think about a calculator. The calculator used to do just simple arithmetic, but over time they become more complex. Now they do graphs, they do all sort of trigonometry, and some of them even they connect to internet. I remember my father used to have one of these old calculator and he was happy with that. But what drives the uh, system or the engineers to design something complex? Maybe the needs for more, let's say, complex calculation and graphing and other things. Can you think about a system that becomes more complex? Here are some examples that when we discuss it in the class, student came up, like cell phone. The cell phone used to be just cell phone, but nowadays, an iPhone, for example, it does everything, and the function of phone is just one simple function of many other functions. Cars becomes more complex, washing machine compared with the old washing machine, buildings, and maybe more examples that you can pause and think about. So we say there are some illities, perhaps reliability, serviceability, producibility, and maybe many other illities, which we refer them, that they are non-functional attributes that drives us to develop more complex systems. Also, sometimes an emergence of a system is something undesirable. We call it an emergency, like an explosion or a fire or a flood. These are all emergence of system, but they are not desirable emergence. We call them emergency. So we can summarize then, there are four types of emergence coming out of a system: emergence of a function, emergence of a performance, emergence of the utilities, and an emergency. Emergence of a function, what the system does. A performance, the system does something better than before. Utilities and non-functional attributes like productability, serviceability, or maybe many other utilities that you can think about. And emergency is something undesirable. Let's look at one example. An hourglass, it shows time. It comprises of sands and funnel, which each of them has nothing to do with time, but you combine them, it does something. It has the function of showing the time, right? However, over time, we made more complex system like this Swiss watch. Perhaps you can pause here and match any of these four types of emergence to one of these examples. AZ, an emergence of a function, the machine learning algorithm. Performance, a restaurant which they use a robot. Utilities, a factory that use systems engineering. And an emergency, a car which breaks. Now we're going to look at the system lifecycle, and we're going to come up with models that makes a systematic way to model a system from concept all the way to the end, to disposal. So going from a need, convert it and a valid need, and then develop a concept, then do the design and development and manufacturing and production and operation and launching, upgrading, and at the end, this end of the life of a system. So, and of course, the role of a system engineer change with at each of these phases. So in the conceptual phase, you need to do the analysis. Going to the engineering development and testing, the focus change and switch to design development and of course the testing. And at the end, the focus of system engineer changed to service and updates, maintenance, and others. Well, let's look at some earlier models. The US Department of Defense come up with a simple model. Look at this model. This is a very useful model that you may apply for your project. In this model, we'll start with a need, a valid need. It doesn't always have to be a need. It might be a technology that is available, come out, and based on that technology, we come up with a new system. In these diagrams, look at the bottom, you'll see three main phases. The pre-systems, or when the system is at the conceptual and a design phase. And then the system acquisition. When you start manufacturing, you do the detailed design and then manufacture the system and then launch the system. And after that, they call it the sustainment. When you do the post-development, when you provide the service to the system that you manufacture. The triangle shows the milestones and the diamond shows the decision points. There are some acronyms, as I showed it at the bottom here, like the PDR, the preliminary design, the critical design review, and so on. So this is a good model that you might adapt for developing, again, any system, and easy to understand. But today we are going to focus on more, let's say, common system development model or system development life cycle, which has three main stages. The first stage, the concept development. The outcome of this stage is to develop a concept to satisfy a valid need. Moving on, the second stage is design and development, or the engineering development. The outcome of that is a validated physical system design, something that we've done the detailed design, we've done the tests, and we validated it. So we are ready to move to the third phase, which is the production. We manufacture the system, we launch it, we deploy it, and then after that, we provide the maintenance, the update, and other services which are required for the system. Another way to look at that, or those three phases, which we refer them to principal stages, are showing them in a diagram like that. So we'll see the concept development, the engineering development, and the post development, the three main stages or principal stages. Look at the arrows at the top. Those arrows shows the flow of information. They start with the need and move to the functional specification, then detailed specification, and then some documentation regarding the maintenance and so on. The arrows at the bottom, they shows the steps going from an opportunity or let's say a concept all the way to a physical actual system that operates. Let's look at one example. Let's say there is a need for a new commercial aircraft. Perhaps we need an aircraft that moves faster. Or maybe a new technology is available, a new material, or perhaps a new engine. So there is a need to develop a new aircraft. So stage one is the concept development stage. So we define a new aircraft concept to meet the market needs and the requirements. Our activity here is to explore different configuration, the number of engines, the size, the shape of the wings. Also, we need to evaluate the cost of the production, the efficiency, the passenger comfort, and maybe we have to do some computer simulation and 3D modeling. Let's say this fancy concept is the outcome of stage one. Now we move on to stage two, is the design and development stage. At this stage, we need to translate our concept into a validated system. It means we need to validate that the new technology works. We need to develop maybe detailed designs or maybe build a prototype, and we have to do some testing. And after that, we move to the post-development stage. After we've done the test, we build a prototype and we've done the improvement. Then we deploy our product, we check its operation, and we check consistently and frequently its maintenance to do the upgrade and also optimize the components that we need. So as you see, the three stages for a simple example like aircraft, how it works. So now let's focus a little bit on details for each of these stages actually. For the concept development, which we have the needs analysis, concept exploration, and concept definition, right? Let's focus on that. We'll start with the need analysis to make sure that the need is a true need, actually. And then we will move to different concept. The more concept we explore here, the better. And then we'll come up, we narrow down our list, and we decide and fix on one concept. So the outcome of the need analysis is to ask, is there a valid need for a new system? Or if there is a valid need, is there a practical approach to that? Let's say there is a need in society for an automatic separate garbage or separator garbage bin. Is there a real need? Yes, there is. Perhaps you are stuck in front of one of these garbage bins to make a decision which hole to put the garbage in, right? You have to read through and make a decision. But what if there is a garbage bin which actually does all the job for you? There is just one hole, like this blue hole, and you put the garbage there and it sorts it out and actually put it in the right bins. So maybe the technology is not yet out there, and maybe one of you can start thinking about how can I implement it? Should I use maybe image recognition, that when a garbage in, I use a camera to take photos and then sort out all the garbage to the right bin? Or maybe a camera and image recognition is not going to be an efficient way, and perhaps there are other ways. So think about a technology that can solve this problem. So the need is there, but maybe the technology is not yet there, or maybe it is, and you can think about it. Now let's move to the engineering development, the second phase. In the second phase, we will focus on one concept. We focus on detailed design. We build the prototypes and we do the testing. So we'll do the test and evaluation to optimize our design and optimize our prototype. The outcome of this phase is the specification, which guide the manufacturer to start building the components. Moving on to the next phase, let's say we launch our product. Now is a matter of mass production, maybe. We have to be aware of the Murphy's Law. Remember in lecture 1 we talked about it? Things may not go as we plan. Maybe there is a strike, maybe issue with tooling, or critical software bugs, and many other unexpected things that can happen. I'm sure you have many examples in your mind. Now it's the operation and support. We need to think about the service. We need to think about the maybe some minor or major updates that our system needs. And now we want to move from abstract to actual components. So perhaps this table can guide us through. Remember in lecture 2, we talk about the level. We break down a system to subsystem, components, subcomponents, and part. Now you can apply the concept development and the engineering design and development for each level. For example, for the concept development, for the need analysis, maybe you have to go to the system level. But at the subsystem, maybe you'll focus on the defined requirements and the defining function. And at the component level, just focus on the function. And of course, in the concept development, there is nothing to do regarding the subcomponents and parts. Perhaps you just visualize how the part may looks like at this stage. But moving on to the engineering development and the design, maybe for the subcomponents, you need to focus on allocating a function to subcomponents and focus on the design. And regarding the parts, there is nothing for other sections, only to make the part, or maybe you can buy it off the shelf. And this table is an example, maybe more applicable to aerospace system development for the airplane examples. On the y-axis shows the level of engagement for a system engineer, for the test engineer, for the design engineer, and so on. So you will see on the concept development, the design engineer involvement, for example, is a little, but moving on to the engineering development, the height of development, which shows on the y-axis, is higher for the design engineer. And moving on to the later phases for the test, you'll see the test engineer is more involved. There are also other methods to show what we discussed regarding these 3 phases and the sub-phases. One is the flow diagrams. These are all the same. Look at actually the flow diagrams. It starts from a need, goes through the requirements, and then you define the functions, and then you allocate a physical component or subsystem to each function, and then move on to the design validation and eventually a solution. And there is a lot of back and forth. So in other words, you set up your requirements at early, and you move on to simulation and testing later. Again, you see there are similarities between this model and the classic model that we just reviewed. And these are very similar to the early DoD, Department of Defense, that we explained earlier, the model they used. And that flow diagram now with more details has been showed in this table I want you to pause this video and go through actually more details and more cells on this table. You see on the first column, you see actually, if I go back, you see these four boxes: the requirement, function definition, physical, and design validation. You see them on the first column. And now you see the concept development and the engineering development that we discussed in the classic model. And you see how they are related to each other. The second model, which is also very common, is the spiral life cycle. And again, this is very, very similar to model one. If I show the four segments of these, you see the requirement analysis, the functional analysis, the physical, and the design validation, right? And this model emphasizes more on the actually the nature of iterative, that at each stage we will keep repeating this. We will always keep repeating and analyze the requirements, the functions, and the detailed design until we get to that optimum design. So one last thing that we need to consider is the environment. Of course, our system works with an environment. If it's a submarine, it works in the deep ocean. If it's an airplane, it works in space, and so on. So I need to have a good, perhaps, simulation of the environment. Maybe I can just use a wind tunnel if it's an airplane, but for the deep ocean, perhaps I need to use maybe a simulation. And after that, we will do the test and analysis. Of course, we will push the boundaries when we do the test to stress the components beyond their capabilities. This is to realize if there is any initial weak spot that we can recognize. We do the tests and we will record everything, obviously. Let's summarize what we discussed. There are three phases or three stages of the system engineering life cycle for any system that we start with a valid need and we plan to materialize it. These three phases are the concept development, engineering development, and then the post-service development. With each stage, there are actual phases. With the concept development, we analyze the need, we explore different concepts, and we define one concept that we believe works the best. And we move on to the second stage, the engineering development. We will do the advanced development, meaning detailed designs and engineering design, and then we will do the integration and evaluation by doing the tests and prototyping. And then we'll move on to the production and perhaps the other service during the launch and during the operation, like the training that we have to do for the new system, the maintenance, and perhaps some upgrades. I'll provide more details here. You can pause the video and go through them, but basically this is what we discussed during the lecture. All right, thank you very much for listening. What I want you to do, think about a system, maybe a simple system, and see how you can apply these three phases and the sub phases to your system of interest. Thanks for listening.